Hello everyone, you're welcome back to Science Arena Academy. In today's video, we are going to take a look at stress that is acting in a body in two mutually perpendicular directions. That means when we have a body like this that is subjected to two forces, let me say here is force P, and then I have this P1 and I have another one here, force P2. Now, don't forget that each of these forces are acting on a plane that is perpendicular to the direction of the force. This one is also acting on a plane perpendicular to the direction of the force. Now, these forces is going to provide a normal stress along this direction and then another normal stress along this direction. Now, if I have a section which is inclined at an angle of theta to the normal direction, which is this normal plane here. Now, this section that is here, this same force P will be acting on this section, and also this force P will also be acting on this section here. These two forces are going to create two different stress on this body, as you have seen in my first initial video. Now, the number of stress that will be on this section will be 2. The first one, the section will be subjected to a normal stress, as you ought to know that, and also it will be subjected to a shear stress. Now, when I was dealing with a body subjected to a single directed force, we said the normal stress that will be in the body should be equals to the stress cos square of theta, the angle of inclination. Please don't forget, the angle of inclination in this case here is my angle theta that is here. Let me try to change the color. So the angle of inclination is angle theta that we have in this place here. While my shear stress, which is your tangential stress, should be equals to your normal stress over 2 into sine of 2 theta. Now, this is my shear stress, while this one is my normal stress that is acting on the body. Now, if we now have two forces that is acting on that body, these two forces develop two different stress. One stress is along the x-axis, and the other one is along the y-axis. Now, what will be the formula for the principal stresses that are acting on the bisected, what will be the formula for the normal stress and the shear stress that is acting on the bisected area, on the section? Now, the formula for it, the normal stress that will be acting on this will be equals to my stress along the x-axis plus my stress along the y-axis all over 2. Now, positive of my stress along the x-axis minus my stress along the y-axis over 2 cos 2 theta. Now, this one is going to give us, this is the normal stress that is acting on the body. Why the shear stress or the tangential stress that will be acting on the body can be easily be given as this. My shear stress on the body will be equals to the sigma x minus sigma y all over 2 sine of 2 theta. Now, these are the normal stress and the shear stress that is acting on the body. Now, let's now take a look at the principal plane. Now, what do we mean by a principal plane? So, let's start with that principal plane. Principal plane. Now, what is a principal plane? Now, a principal plane is a plane of maximum shear stress. Let's assume that. So, when we say the principal plane, it's a plane in which the total shear stress that is there is equals to 0. It simply shows that what? To get a principal, at what angle do we have principal plane? Now, our principal plane is always at an angle of this. Assuming we have my shear stress to be equals to sigma x minus sigma y all over 2 sine of angle 2 theta. Now, I said for principal plane, a principal plane is a plane of 0 shear stress. Simply means if this shear stress here is equals to 0, I should be having all this to be equals, I'll be left with sine of 2 theta equals 0. That's what I'll be left with here. Now, if my sine 2 theta is equals to 0, then the value of this theta can either be, my 2 theta will be equal to sine inverse of 0, which can give rise to 90 degree. Now, sine inverse of 0 is equals to, sine inverse of 0 will give rise to 180 degree, or I have what? 0 degree itself. So, my sine inverse of 0 can easily give 180 degree or 0 degree. Now, this 2 theta here represents my principal plane. That means a plane in which the total shear stress that is there is equals to 0. Now, from here, I can easily calculate this out to get my value of theta. That my value of theta will be equals to either 90 degree, or we can have 270 degree. That is, so principal plane is a plane in which angle theta is 90, or it is equals to 270 degree. These are what? My principal plane. Now, that's for that. Now, you now see, if I have a principal plane, let me assume that this plane here is a principal plane. This is a principal plane. Now, a stress that occurs on a principal plane is known as a principal stress. We call the stress that take place, okay, let me say this is a plane of principal plane. Now, the stress that occur on the principal plane are known as what? The principal stress. I can have the maximum principal stress, and I can have what? The minor principal stress altogether. Now, don't forget something that we said. For a principal plane, principal stress only take place on the what? Principal plane. Now, these are my principal stresses, sigma 1 and sigma 2. Now, let's take a look at something again. Let me remove this. Now, we want to have maximum normal stress. Now, maximum normal stress, I'm trying to take it one by one so that you can understand. Now, maximum normal stress. Now, when do we have maximum normal stress? And when do we have maximum shear stress? You see, the normal stress is said to be maximum altogether when the value of cos 2 theta is equals to 1. Then we have a maximum normal stress altogether. So, maximum normal stress is said to be what? Maximum when cos 2 theta is equals to 1, or when theta is equals to 0. So, when my value of theta is equals to 0, we have a maximum normal stress altogether. Now, let's take a look at this here. Now, from here, I can have, from the formula of normal stress, my formula of normal stress, I have normal stress to be equal to sigma x plus sigma y all over 2. Then positive of sigma x, minus sigma y over 2. Then cos 2 theta. Now, if this my cos 2 theta is equals to 1, I should be having something of this. I'll be left with my normal stress, which is maximum, is equals to sigma x plus sigma y. This is over 2 plus sigma x over 2 minus sigma y over 2. Now, this can cancel this, and whereby my maximum normal stress will be equals to sigma x. Simply means maximum normal stress only take place along the x-axis. Now, what about my maximum shear stress? When do we have maximum shear stress? You see, maximum shear stress only take place when my angle of sine 2 theta is equals to 1, or when theta is equals to 45 degree. So, when value of theta is equals to 45 degree, we have the maximum shear stress. Or let's say when 2 theta also equals to 90 degree. So when 2 theta is equals to 90 degree, we have the maximum shear stress. And when theta is equals to 45 degree, we also have the maximum shear stress. Let's take a look at the formula for maximum shear stress. Now, maximum shear stress is always, since this is my shear stress, let's put maximum so that we can indicate, is equals to sigma 1 minus sigma x minus sigma y all over 2 sine of 2 theta. Now, since for maximum shear stress to take place, sine 2 theta must be equals to 1, then the maximum shear stress will be equals to sigma x minus sigma y all over 2, which is all this one will be equals to 1. So this is the formula for maximum shear stress in a material. Now, in my next video, we're going to take a look at examples on how we can solve problems by using these formulas one by one. Thanks for watching this video. Please don't forget to subscribe to my channel and like my video. Thank you.